Hello everyone, welcome to DP Tutorials by Donny Jerwa. In this teaching module, we will accentuate and emphasize on another application of Savart's law, which is to find the magnetic field on the axis of a current carrying circular loop. So when we look at this figure, this is a circular coil, or we can say a circular loop having a radius r. So in this main diagram, I have written in such a way that I have resolved all the rectangular components related to the magnetic field due to the current element. So in order to understand the real concept about how we can find the electric field due to that circular loop, let us discuss in this preceding section. So on this preceding section, okay, we have this circular coil, and this circular coil is a coil, or we can say a loop. That means any loop having a radius r. So that is the first thing. Okay, we have a circular coil where the radius of that circular coil is r. So let r be the radius of this circular coil. Now we know that in order to find when the current is flowing, let the current I be flowing through that circular coil. Okay, and since this is the circular coil, we can divide this coil into many current elements. Okay, I can divide this into many current elements. All these current elements will be having length dl, will be having length dl, and it will be having length dl. So we have also emphasized in the previous section that if I want to find the current due to this coil, that means I have to take into account the circumference of this coil, and the circumference of this coil, if capital R is the radius of that coil, which means that the circumference of the coil will be twice pi r, which in this case means that if I integrate over that small elementary length dl, that means over here, that means it will be the circumference of the coil, and that circumference of the coil will be equal to what? Twice pi r. So that is the main reason. So over here, let I be the current flowing through that coil, and across this coil we can divide, or we can construct many current elements. So we can consider many current elements. Those are our current elements. So from here, this is also what? A current element. So I will consider, suppose from here, if we want to find the magnetic field along the axis, that means over here, if I orient this coil on the xy plane, that means from here, suppose let us consider that this is the x-axis, this is the y-axis, and this is the z-axis or the z-axis. So from here, which means that if I want to find the magnetic field due to the coil along the axis, suppose if I draw a line which passes to the center O of the coil, that means this is our axis. Okay, x dash is our axis. So which means over here that this is the center of the coil, and we have placed this coil in such a way that it is lying on the YZ plane. Okay, the coil is lying on the YZ plane, and this x-axis is the axis which is perpendicular to the coil. Okay, this x-axis is the axis which is perpendicular to the coil. So from here we will consider two current elements, one from the upper portion and one from the lower portion. We will consider two current elements, one from the top and one from below. So from here, these are our current elements. Since this is the direction, since this is the taken direction of our flow of current, so from here current I will be moving on this direction. Then if dl is the length of that conductor, then this is what? This is our current element. And when from here the current is moving on this direction, so the direction of our current element will be on this direction. So this will be what? Let dl, okay, let dl be the length of that element. So from here we will represent these elements in this direction. This will be the current, this will be our current element directed on that direction, okay, idl. And from here also this will be the direction of our what? Of our current element. So again, from here, Okay, let me try to make this a little bit longer. Okay, so this will be our current element. So we will take this current element and we will place it over there. So this is our current element IDL. This will be, when you look it carefully from here, our current element is directed on this direction, and the current element on the upper portion is directed on this direction. So along this x-axis, okay, let us consider a point P. Okay, let us consider any point P which is along the x-axis. So if this if P is the point along the x-axis which is at a distance x, okay, which is at a distance x from the center O of the circular coil or circular loop carrying a current I, then I want to find the magnetic field. Okay, I'm interested in finding what is the magnetic field B of the coil at the point P, which is at a distance x from the center O of the current element. So this is our target. We want to find the magnetic field at B due to the current carrying loop carrying a current I, which is at a distance x from the center O at a point P along the x-axis. So from here, how will you find that magnetic field at P due to the current element? So from here, if this is the current element, then what I have to do, I have to consider radius vector of the current element up to the point P. So let this be the radius vector of the current element up to the point P. So over here, this will be the radius vector of the current element this will be the radius vector of the current element at the point P. So this will be what? This will be our R bar. And even there will be current element from the bottom of that circular coil. So I will consider this as what? This is as our radius vector. So this will be the radius vector. This will be the radius vector from this point up to R. This will be the radius vector from this IDL up to point P. This will be the radius vector from IDL up to point P. So this will be what? This will be our R bar, and the direction will be in this direction, and the direction will be on this direction. This will be what? This will be your R cap vector, and over here also this will be your R cap vector. Okay, the direction from the current element up to the point P. Then from here you have to find what is the magnetic field at this point P. So how will you find the magnetic field at this point P? So we have to apply this right hand palm rule. Okay, right hand palm rule. So over here, when you look at this right hand, you have to place your right hand. Okay, you have to place your right hand in such a way that your right hand at this point P is okay, in which if you look at this particular point, that means this will be the direction. You have to place your right hand in such a way. So you have to place your right hand in such a way that your palm, okay, your palm is facing up. Your palm is facing up. I will consider the magnetic field due to what? Due to this upper part of the coil, or due to that upper element of the coil. Okay, due to that upper element of the coil. Okay, that upper element of the coil, will be this part. Okay, that upper element of the coil will be this part. And also we will consider the magnetic field due to the lower element. So due to the upper element, I will make use of this right hand palm rule, in which you have to orient your hand, or you have to align your hand in such a way that it should point in the direction of your current element. So when you look at this right hand over here, I have placed this thumb in such a way that this thumb is pointing along the direction of what? Of the current flow. So from here also, I will place this thumb in such a way that that thumb is pointing in the direction of what? Of the direction of the current flow. And this projected or outstretched fingers, the outstretched fingers will be in the direction of what? The outstretched fingers will be in the direction of your radius vector. Okay, the outstretched fingers should be in the direction of your radius vector. So from here, I outstretch this finger in the direction of what? Of my radius vector. So the direction in which the palm faces. Okay, so this is the direction of our current I. Okay, this is the direction of our current I. I place the thumb, and the outstretched fingers will be the direction of what? The outstretched fingers, this will be the current element IDL, and the these outstretched fingers will be the direction of R. Okay, that will be your R bar. So our thumb, that means this palm is perpendicular. Okay, the palm is perpendicular. So which means that at the point P, okay, our our dB will be perpendicular and upwards, which means at this particular point it will be perpendicular and upwards. So let us again rephrase that sentence. So from here I will take this vector and let this vector be what? Let this vector will be our ideal vector, and this vector, this purple ray, this yellow ray or yellow line will represent what? This yellow line will represent our radius vector. This will be our radius vector. This will be our radius vector. Yellow line representing the direction of our outstretched fingers, radius vector, and this red color line indicating the direction of the thumb, which indicates the direction of what? Of our current element. So our current element is in this direction. The current element in this direction of the current element, and this is the direction of one. This r bar is the direction of what? Radius vector pointing at this direction, which means that at this particular point our palm is facing upwards, so that will be the direction of B. So which means that at this particular point our B will be on this direction. So that will be one. That will be the direction of B. So B in this case will be perpendicular and upwards. So at this particular point, the magnetic field will be pointing upwards. So it will be directed by, it will be represented by the dot. So over here, magnetic field will be perpendicular due to the upper element. It will be perpendicular and upwards. Direction of B due to the upper element, or due to this upper part of the circular coil, or due to the upper circumference of the coil, or due to half of the coil, or due to the upper circumference or the semicircle, will be upwards. Then similarly for this lower part of the coil, if you look at the lower part of the coil, that means from here the current element is in this direction. So from here I have to take the palm of the right hand. This palm of the right hand should face in this direction, which means that if you look in this case, your right hand, the palm of your right hand is facing down. The palm of your right hand is facing down. Let me write it properly. The palm of your right hand is facing down. So palm down. In this case, the palm is down. And when the palm is down, you have to orient your fingers in the direction of I. I is moving on this direction. So that will be what? This will be the direction of what? This will be the direction of I. So this is our direction of I. I is on this direction, our current element, since this is the direction of the current. So from here, the direction of the current element in this direction, so that will be our ideal vector. And from here, this will be what? This will be the direction of our radius vector. Okay, the outstretched fingers in the direction of the radius vector. Since this palm is facing down, so the direction of magnetic field will be perpendicular and downwards. So which means that over here, if we want to represent this direction very carefully, if I want to represent that direction carefully, so from here, let us take this red colored, line representing the direction of our ideal vector. This will be the direction of our ideal vector. That will be the direction of our ideal vector. And this yellow vector will indicate the direction of our radius vector. So from here, this is our ideal vector pointing in this direction. This is the direction of our ideal vector pointing in this direction. Similarly over here also, this will be the direction of our ideal vector. And the outstretched fingers is in the direction of your R bar. So I will take this vector, and that this yellow colored line representing the direction of our R, R bar. This is the direction of our radius vector and pointing in this direction, and this is the direction of our ideal vector or current element vector pointing on this direction. Since your palm is facing down, at that particular point, since the palm is facing down at that particular point P, which means that your current element will be downwards. Over here, the direction of the direction of dB will be downwards. The direction of your dB will be downwards. So from here, I will take, that means at this point B, the direction of that current and the direction of the magnetic field at that point will be what? Will be perpendicular and downwards, and it will be represented by the cross mark. So from here, I will take this vector. This will be one, the magnetic field vector. The magnetic field vector will be perpendicular and downwards. Why is it perpendicular and downwards? Because your palm is facing down. So at that particular point P, that means the magnetic field due to this one, due to this current element from the lower part, okay, from the lower part of the coil, it will be pointing perpendicular, okay, perpendicular and downwards, okay, perpendicular and downwards. So from here there are two, okay, there are two one. There will be two magnetic fields due to the upper part and the lower part. So from here, when you look from this particular diagram, that means at this particular point P, you will have what? You will have two, what? You will have these two radius vectors. So from here, this will be the dB. This at this particular point P, this will be the magnetic field due to the current element from the upper part, and we will have another due to the lower element. I will have another dB. This dB will be pointing in what? This dB will be pointing on this direction. So that will be the direction of what? That will be the direction of dB. So this will be the direction of dB. Okay, this will be the direction of dB. So from here, when you look at that particular diagram, okay, when you look at this particular diagram, this dB, okay, is we have to resolve. Okay, you have to resolve. Okay, what did I say? We have to resolve the direction of dB. Okay, we have to resolve dB into different components. Okay, so from here, let the direction of the radius vector, this is the direction of the radius vector, which makes with the x with the direction with which the coil makes with the point P, this will be what? Let that angle be theta, and let this angle also will be theta. So if this is theta, which means that this angle over here, since this full angle is 90° minus theta, it implies that that if I want to find this angle will be what? This angle will be equal to theta, which means that this full angle will be how much? Will be 90°. If you look, if I rephrase again, okay, if I rephrase again my teaching point, okay, my teaching point. So if this is theta, then this remaining angle, what will be that remaining angle? That remaining angle will be 90° minus theta. So I'm interested in finding this angle. I'm interested in finding this angle. So what will be this angle in the question mark? So over here you have the angle will be like that. So from here this will be one line, and this will be another line due to dB. This will be that line due to R. If you look at this small angle over here, what is that angle? That angle will be 90°. If you try to prove, you will find out that this angle within this question mark, that angle will be equal to how much? That angle will be equal to theta. You work out the mathematics by yourself. So from here, this angle will be theta, and also that angle will be theta. So you want to find, okay? So resolving the value of dB, that means you have to know what will be the component along this direction, which is along that direction, and you also have to know what will be the component along this direction. Of this dB from the lower part, you have to know the component of dB along the x direction, and you have to know the component of dB along the y direction. Okay, so from here, finding those perpendicular components, along the vertical component and along the horizontal component, you have to consider in some of the triangles. Okay, in some of the triangles. So from here, if I want to solve for this particular part, okay, I have when you look at that particular figure, only at this particular part, that means this will be the direction of what? This will be our line, and over here this will be the direction of what? This will be the direction of our dB. So this is our dB vector. Okay? dB vector. So from here, if I try to complete this figure, that means I will get what? A right angle triangle. And from here, if this is theta, it means that that angle is also what? That angle is also theta. And this will be what? Equal to 90°. So this is dB, and I want to find this. What is this? This component will be our that component will be our perpendicular component. Okay? This will be our perpendicular component, and this component, which consists of the angle 90° and theta, this will be what? This will be the base component. So if I want to find the perpendicular component and the base component, that means I have to do what? I have to consider I have to use trigonometry. So how will I use trigonometry? Yeah, how will I use trigonometry? So from here, if I use sine of the angle, okay, sine of the angle will be what? Perpendicular divided by base. Okay, perpendicular divided by base. Some people have, okay, perpendicular by hypotenuse. I mean, so what is our hypotenuse? Our hypotenuse is over what? Our direction of dB. So from here, for finding the perpendicular component, it will be hypotenuse into what? Hypotenuse into sine of theta. Okay, hypotenuse into sine of theta. So what is this hypotenuse? Hypotenuse is nothing but this dB. So the perpendicular component will take the value of what? dB sine theta. Okay, this perpendicular component, that means this component over here, this perpendicular component will take the value of how much? That perpendicular component will take the value of dB sine of theta. And this dB sine theta of this particular component, this will be acting on this direction. So if you look from this figure, that means the dB component, that means this dB component from here will act on this direction. And that dB component will be what? That dB component will be what? Will be dB sine of theta. So this is that, or dB sine theta. This is that magnetic field dB. Okay, magnetic field dB. So this will be dB sine of theta. dB sine of theta, which means I can represent that by this vector. Since I can represent, if I can remake this figure, that means I can get what? A rectangle. Okay, I can get a rectangle. So if the upper part is dB sine theta, if the upper part is dB sine theta, which means that the lower part also is what? dB sine theta. So this will be that component dB sine theta from the lower part. Then I have determined the perpendicular component. Next, I will determine the base component. So how will you determine the base component? So another function, first function for determining the perpendicular component is using the sine function. Next thing, that if you want to find the base component, you will have to make use of what? Of the cos. Okay, cos of the angle, or cosecant of the angle. So cos of theta will be what? Base divided by hypotenuse. So from here, that means our base will be what? It will be hypotenuse into cos of theta. And what is the hypotenuse in this case? The hypotenuse is nothing but our value of dB. So over here you write what? dB cos of theta. So this will be what? This will be our base component. So the base component in this case, is acting in the upward direction. So this value of the base component will take the value of what? dB cos of theta. So if you look from that upper diagram with what we have solved from here, see, from here the direction of dB sine theta is along this direction. That is why I have represented by this vector. And the direction of our dB cos theta will act in the upward direction. Okay, it will act in the upward direction. So this will be the direction of what? This will be the direction of what? Of this dB. This direction will be what? This direction will be dB cos of theta. So that is the way. So we have resolved the components. Okay, I will drop this part because it will be not necessary. So from here, that is the component dB cos theta due to the upper element. So from here, this, what will be this? This will be what? This component will be dB, okay? dB sine of theta, acting along which direction? Acting along the x-axis direction. Similarly, from the lower part, this dB, okay, this dB from the lower part. Again, you have to consider, okay, in the same. If I do over here, that means this is the direction of what? This is the direction of what? This is the direction of what? dB. Okay, this is the direction of what? dB. And from here, this is the perpendicular part. And from here, this is what? This is your angle theta. That means if I keep on solving this part, that means if I complete this triangle, that means what will I get? I'll get a right angle triangle, which means that this is the 90 degree, which convinces us that this will be our perpendicular and this side will be what? This side will be our base. Similarly, for finding the perpendicular, that means this perpendicular will take the value of 1. If we solve, that means we'll get dB sine of theta, and this dB sine of theta will act on which direction? This dB sine of theta will act on this direction. So this dB sine theta will act on what? On this direction. So from here, that means if I try to complete this figure, okay, if I try to complete this figure from the lower part, that means what will I get? I'll get a rectangle. So the opposite sides of rectangle are parallel and equal. So I can represent by this vector. Okay, this vector, that means this vector will be dB sine theta from the lower element. Okay, so this will be what? This will be dB sine theta from the lower element. Okay? dB sine theta from the lower element. Okay. So we have to be very, very careful while resolving vectors. So that is the idea. Okay, with clear, intriguing concepts. Okay, your concepts should be crystal clear. Then next part. Okay, next part is we want to find the base component. In order to find this base component, that means the direction, the component will be of the value of 1, the value of dB cos of theta. Okay, dB cos of theta. And since this dB cos of theta is acting on this direction, so which means that the dB cos theta, this dB cos of theta will act on what? On this direction. This is the direction of dB cos theta, which means due to the components of dB along the vertical direction is dB sine theta acting on this direction, and the component of this dB due to that lower element of the horizontal component, which is dB cos, this dB cos is acting on this direction. So this will be the direction of what? This will be the direction of what? dB cos of theta. So this is what? This is dB cos of theta. So this is dB cos of theta. dB cos of theta. So that is the way how to solve those important steps. So from here we have got these values. When you look at this particular analysis of our figure, which means that over here, the direction of dB cos theta is acting in this direction, and the direction of our dB cos theta due to the lower element is acting on this direction, which means that they are opposite. Okay, they are equal and opposite and acting in opposite direction, which means that they will not account for the total magnetic field. So they will cancel each other's effect. What are the two vectors which acts on the same direction? These are the two vectors which acts on the same direction. So the total magnetic field, okay, the total magnetic field due to this entire coil will be purely due to this component. It will be purely due to this component dB sine of theta. Okay, dB sine of theta. So this will account. Okay, this will account for the total magnetic field at the point P due to the current element. That means from the upper part of the coil, it will be dB cos theta will act perpendicular upwards, and from the lower part of the coil, the direction of dB will be acting perpendicular and downwards. So just go through that so that you will understand. And now we will just move on into the derivation. Okay, into the derivation. So from here, I have written very, very clearly that this will be dB sine theta and dB sine theta acting on the same direction, and dB cos theta acting in opposite direction, so they will cancel each other's effect. So this will be the direction of our current flow. Okay, that will be the direction of our current flow. So this will be the direction of our IDL vector, and from here the current is moving in this direction, so this will be the direction of our IDL vector. Okay, so from here this will be the direction of our radius vector, and from the current element to the point P, this is the direction of our radius vector. Even from here, the position vector will have the distance of r bar, the position vector will have the distance of r bar. Okay, and even from there also you will have to find the value of r, okay, which we can do that. So from here, let us consider a current. Okay, let us consider a current carrying coil carrying a current I, as shown in the figure. placed in what? Where is this coil placed? This coil is placed on what? On the YZ plane. Okay, this is the YZ plane. It is perpendicular to the x-axis. So it is placed on the YZ plane. And let 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 P be the point. Let P be the point on the x-axis. This P is the point on the x-axis, which is at a distance what? Which is at a distance x from the center O of the coil along the axis. So from here you will consider two elements like one I have explained, one from above and one from below the coil as shown in the figure. So this is below and the upper one will be from above. Okay? This will be from below the coil, this will be from the above the coil. So from there, it is very obvious that this angle here, the current element ideal and that radius vector are always perpendicular to each other. So when you look over here, okay, that means it is very obvious that this current element, that vector current element, and with this radius vector and what that radius vector, this current element, okay, this radius vector and the current element ideal are perpendicular to each other for both cases, both from the upper part and both from the lower part. Even from the lower part also, the radius vector and the current element are perpendicular to each other. If they are perpendicular to each other at the point P, so it means that it is perpendicular to the one. It is perpendicular, and at point P is perpendicular to the plane containing the ideal and R vectors. Okay. So from here we have to resolve. What do you have to resolve? You have to resolve that dB. Okay, the components of dB. You have resolving the components of dB at P due to the current elements, one from the above and one from the below. You will have to resolve that. So what was the perpendicular component? This dB sine is our perpendicular component. This dB cos is our horizontal component. So the perpendicular component is what? We will just write over here. The perpendicular component will be dB sine of theta. So both these are acting along what? Both these are acting along the x-axis. And from here also I have explained that this dB sine theta, since this dB sine theta, both these are acting on what? From the upper portion acting in the same direction, from the lower portion also acting in the same direction. So they will contribute. Okay? They will contribute to the what? To the resultant magnetic field at point P directing outwards. Okay, this is the direction outwards. But that dB cos, okay, this dB cos, one is directed downwards and one is directed upwards. That means they are in opposite direction. This dB cos and dB cos are acting in opposite direction, so they will cancel each other's effect. Okay, so they will cancel each other's effect. So from here, the horizontal component is what? The horizontal component is dB cos of theta. Both these are acting in the opposite direction and they will cancel each other's effect, and hence they do not contribute to the total magnetic field at that point P. Then from here you have to apply Biot-Savart's law. So what is Biot-Savart's law? You have to just write it here. Biot-Savart's law is given by that relation, okay, dB, okay, dB equal mu naught divided by 4 pi. So dB will be equal to mu naught divided by 4 pi. Okay. dB is equal to mu naught divided by 4 pi ideal cross r bar divided by 1 divided by r cube. This is the vector form of 1. This is the vector form of our Biot-Savart's law. Okay, this is the vector form of our Biot-Savart's law. But from the figure, it is very obvious that ideal, okay, that ideal and r bar, okay, are on the 1. That ideal and r bar are on the xy plane, okay, and are perpendicular to each other. So if they are perpendicular to each other, which in this case, okay, I can write in this case, what is this? This is our direction of r bar, okay, What is that? That is the direction of r bar. Okay, from here, this is the direction of r bar, this is the direction of x, and this is the direction of, this is our radius of the radius of what? Radius of that circular coil. So from here, which means that this will be the radius of the coil, and this will be the x. Okay, that will be x. I'll just write it in magnitude. So from here, this will be 1. This will be 90 degree, and that will be 1. That will be angle theta, which means that and this is 1. This is the point P. And from here you have that current element. Okay, that current element is in that direction. This is the direction of the current element, and the current element, this direction, this will be our 1. This will be our current element. This current element ideal is in this direction, which means that r bar and ideal, they are perpendicular to each other. Okay, perpendicular to each other. So I want to find this value of r. How would I find this value of r? Using Pythagoras theorem. If you use Pythagoras theorem and that right angle triangle, okay, we can calculate the value of r. Since r is the hypotenuse, so r square on the hypotenuse is equal to the sum of the squares on the two sides. So we have x square plus r square. And if we want to find only for r, it will be 1. Only the hypotenuse will be r square, x square plus capital R square, okay, root over that condition. So from here, it is very obvious that we have to write that dB in the scalar form. So when you write this dB in the scalar form, it will be mu naught divided by 4 pi, okay, I dl, okay, I dl. Then you have to write what? R cap r sine of theta. Why we write like this? Okay, why we write like this? Divided by 1, divided by r. Okay, why we write like that? Because we know that the direction of this is the concept of the unit vector. Okay, r bar divided by r. So if I want to find only r bar, so it will be 1. This r bar will be equal to r cap into r. Okay, that r bar will be r cap, because multiply this r both sides, will get r. But since this is the cross product of two vectors, so you have to write what? Sine, because a cross b will be equal to 1, will be equal to ab sine of the angle between the two vectors and the unit vector, which in this case it means what? It means that we have IDL cross r bar. This will be that context, IDL and r bar. Okay, this from the numerator term. Okay, from the numerator term we have what? We have IDL cross r bar. So this IDL cross r bar will give you the value of what? IDL. Then if you replace this r bar, if you replace this r bar by this expression, so you'll get what? You will get, if you replace that r bar by that expression, so I will write here properly, this will be equal to 1. This will be equal to I dl. In place of that r bar, put by that this equation, so you'll get r cap r, and with 1, with that sine of 1, sine of theta. So that is why it gives us this relation. And from here, after you keep on solving, okay, after you keep on solving, you will come to this another step, mu naught divided by 4 pi, okay, mu naught divided by 4 pi I dl. Then r and 1r will get cancelled, so IDL sine theta, IDL sine theta divided by 1, divided by r square. Over here, since the value of r cap, okay, the mod of r cap will be equal to 1. Okay, that is the concept of unit vectors. So next from here, okay, we know from the figure, okay, that is, I can write over here in short, that is dB. Okay, this dB will be equal to 1, mu naught divided by 4 pi, okay, I dl, okay, I dl sine theta divided by 1, divided by r square. But from the figure, okay, from the figure, what do you get over here? What is this value of r? From the figure, the value of that r, okay, the value of that r will be equal to 1. Okay, the value of that r, hypotenuse r square, will be 1, will be equal to x square plus 1 plus r square. Yes or no? X square plus r square, which means that this term in the denominator term of our equation 1 takes the form of, which means that over here we can imply that equation 1 can be written in this form. That means dB, okay, dB will be equal to 1. Mu naught divided by 4 pi, okay, mu naught divided by 4 pi, ideal divided by 1, divided by x square plus r square, using this expression, okay, using that expression. So we can mark this as equation number 2. But the resultant magnetic field at point P is due to 1, is due to that component dB sine of theta. So dB sine of theta acting along the x-axis, which means that this magnetic field, okay, this magnetic field is purely due to 1, due to our dB sine of theta, okay, dB sine of theta. So this will be dB sine of theta, our total magnetic field. So from here, this total magnetic field in this case, that means over here we can find out in this way, okay, this will be dB. What is the value of dB? The value of dB, which we have solved from equation 2, that is substitute over here. This will give you what? Values of mu naught divided by 1, divided by 4 pi, okay. IDL from equation 2, that means this will give you x square plus r square, okay, x square plus r square into sine of theta, x square plus r square into 1 sine of theta, sine of theta. So let us just review from the lower element. If you look from the lower element, that means from here also, this will be the radius of the coil. If we look from that main diagram, okay, if you look from that main diagram, that means from here, this distance also will be 1, this distance will be r, that will be x, and this will be small r. So this is your current element, okay, that is your current element. So if you look from the, with respect to the lower current element, so from here, if you look at this particular point, this will be your current element, okay, that will be your current element, and acting on these directions, which means that from here, this angle also will be 90 degree. This is your IDL vector, okay, IDL vector, and this is your what? This is your R vector, and this is your X vector, which means that this value of R over here also, this value of R over here will take the value of x square plus what? X square plus r square. This is the angle theta, and this is 90 degree. So next from here, you have to find what is this value of what? What is this value of sine of theta? We know sine of theta is what? Perpendicular by hypotenuse. So you can solve for both the triangles the value of what? Sine of theta. So we have sine of theta. This sine of theta will be what? What is the perpendicular? In this case, the perpendicular will be what? The perpendicular will be this radius. So the perpendicular will be the radius, and the hypotenuse will be what? The hypotenuse will be that value of x square plus r square. Similarly, over here also, what will be the perpendicular? The perpendicular in this case will be this r. This radius of that coil will be the perpendicular. This value of r will be what? Will be your hypotenuse. Okay. So from here, the value of sine theta will be perpendicular by hypotenuse. Also, I'll write capital R divided by what? Divided by root over x square plus capital R square. So in this case, I will write this radical sign in terms of what? In terms of power form, which is x square, okay, x square plus r square, okay, plus r square to the power 1 by 2. So let us mark this as equation number 3, which means that equation number 3 reduces to, okay, equation number 3 reduces to, okay, equation number 3 reduces to dB equal mu naught divided by 4 pi, okay, I dl divided by x square plus r square into, then what is the value of this sine of theta? The value of this sine of theta, making use of this equation, it will be what? It will be r divided by x square plus r square, okay, x square plus r square to the power 1 by 2. And if we keep on solving this expression, this value of dB will be equal to mu naught divided by 4 pi, okay? Mu naught divided by 4 pi, mu naught divided by 4 pi. So I will take this r over here, IR dl, and the denominator term, okay, and the denominator term we can write in this form. Okay, we can write in this form because the power of this expression is like 1, and this will give you what? The total of 1. The total power will be 3 by 2. Okay, how is that possible? 3 by 2. Okay, how is that possible? 3 by 2? Because from here, that means you have x square plus r square, okay, and then you multiply another term which is x square plus r square, and this will be 1. This will be to the power half. So using law of indices, we have x square plus r square, okay, and then you have over here the power of this will be 1, and from here this will be 1 by 2. If you add this, then you get this equation. So let us mark this as equation number 4. But we have also discussed that the net contribution, okay, the net contribution due to this circular coil, from all the current elements, okay, from all the current elements, all those are the current elements, it will be purely due to what? Due to this component dB sine of theta acting along the x direction. So acting along the x direction, which means the unit vector will be what? The unit vector will be I cap. So in this case, the total magnetic field, okay, or the net contribution is obtained by what? Is obtained by integrating the above equation 1, equation 4, and its direction is along what? Is along the x direction, which means that is, okay, we have to integrate over this dB, okay, we have to integrate over this dB, and this integration of dB will be along what? All this dB will be along the x direction. So I will write integration over dx, which means that integration of dB will give us what? Will give us the value of b. Okay? Will give us the value of b. And from here, that means this will be integration. Let us put that direction of I cap. Okay, let us put the value of I cap. So it will be like that. Then what is this value of I cap? This value of I cap is our one, is our unit vector acting on that direction, okay, acting on that direction. So over here, that means therefore this b will be integration of 1. That means when you integrate, you have to integrate this equation 4, then you have to put that value mu naught divided by 4 pi, okay, I r dl divided by 1, divided by x square plus r square to the power 3 by 2. But when you look from this figure, that means mu naught, 4 pi, even the current, even the radius, even that value of x, all those are what? All those are constant. When you look from that figure, okay, when you look from that figure, that means the current I is constant, the radius of the coil is also constant, even this x also for the point P is constant, okay, and this radius r is also constant. What is different? The difference is only this dl. So if you sum over that dl, which gives us what, which I've explained previously, that it will give us the circumference of the coil. Okay, the circumference of the coil. So which means from this expression, that means we can take mu naught outside, and then we are left with 4 pi, and over here current also we can take outside, the radius also can be taken outside of the integral sign, the denominator term also can be taken outside of the integral sign, then we are left with this expression, okay, this will be equal to 1, 3 by 2, okay, to the power 3 by 2, so this will be to the power 3 by 2, so 3 divided by 2, so it will be integration over dl, but this integration over dl will be equal to 1, will be equal to twice pi capital R, which is 1, which is the circumference, okay, circumference of 1, the circumference of that circular coil, or the length of the circular coil, length of the loop or circumference of that coil. So from here we can simplify. Okay, we can simplify this expression in this form. This will give us mu naught divided by 4 pi. Okay, this will give us IR divided by 1 divided by x square plus r square to the power 3 by 2 into twice pi r, which is the value of what? Which is the value of line integration of dr. So from here, if you keep on solving, that means pi and pi will get cancelled, 2 and 2 will get cancelled. So you will get the expression of mu naught divided by 2. Then r and r, we have I. R and r, if you multiply, that means we give you I square, r square I mean. And from here, this will be what? This will be the expression for the magnetic field, okay, for the magnetic field of a circular coil along the axis. This will be the magnetic field of the circular coil along the axis. Okay, this will be that expression, general expression. So this will be the expression of the magnetic field due to the current loop at the point P along the x-axis. That means when you want to find along the x-axis. Now let us put another assumption. Okay, another assumption. We have this coil and the point P is over here, which is at a distance x, and this is the center of the coil and this is the radius r. So let us consider this point P to be located where? Let this point P be located at the center. So if this point P is located at the center, if we take that point P to be located at the center O of the coil, which means that this value of x will what? Will reduce to 0. It will reduce to 0. That will be the special case. Okay, that will be the special case. From here, let us consider the case in which what? In which the point P, okay, in which the point P is located at the origin O. So when the point P is located at the origin O, common sense tells us that value of x will be equal to 0. So what happens when value of x equal to 0? What will that final resultant equation gives us? What will this equation which we have derived over here give us? What will this equation give us? Okay, so when x is equal to 0. So when x is equal to 0, it means that the point P is located where? When x is equal to 0, it means that the point P is located where? The point P is located at the center O of the coil. So which means that if I mark this as relation number 5, therefore the magnetic field at the center of the coil, the magnetic field at the center of the coil will be given by what? B equal what? B equal mu naught divided by 2. Over here we have what? We have I r square. Then over here this will be 0. 0 square of 0 will be 0. Then we have r square, and over here you have that term 3 by 2. And if you keep on solving further, okay, if you keep on solving further, you'll get this expression. Okay, mu naught divided by 2. Over here you will have what? You will have IR square. Then over here you'll have r square to the power 1 to the power 3 by 2. This 2 and this 2 will get cancelled. So you will get what? You get an expression of this form. Okay, you get an expression of this form, mu naught divided by 2 I r square divided by 1 divided by r cube, which means that r square and that r cube can be cancelled, which gives us the final expression, which reduces to the magnetic field of the coil IR, okay, r square and r cube will get cancelled, so you get IR mu naught I divided by 1 divided by twice pi. This is that expression which we have derived previously, okay, that this is the expression for what? For the magnetic field, okay, magnetic field of the circular coil. Okay, this is the expression for the magnetic field of the current carrying circular coil at one, at the center of the coil, okay, at the center of the coil. So this is the expression. If the coil has only one term, it is given by this expression. But if the coil has n turns, that means you multiply by n, then you will have what? Mu naught ni, okay, mu naught ni divided by 1 divided by twice r, where r is the radius of that coil. So just go through these lectures which are very, very important. See, from here also it reduces back to that expression which we have discussed previously. So just go through these important things that we have discussed so that you'll get a clear concept relating to physics. Okay, revise on all those terms which we have discussed pertaining to resolution of vectors. Until we meet again, thank you.